So
I think question has popped up.
what explanation you require about simulation and synthesis? Both of them are quite wide topics. Quite wide topics means like uh, synthesis would be covered in session 4. Session 4 ni module 4. So in module 4, synthesis would be covered in more detail. So there you will see how high level synthesis will work. So in first half, I gave you some overview that how typically high level synthesis works. And logic synthesis is it is translated. So you have seen the Verilog code now. So in Verilog, you have two kind of codes. You see, one is clearly data flow, another is behavior one. In data flow, your synthesis tool need not to be very smart. It will take these operations and there is almost one-to-one correspondence with the hardware. In high-level synthesis, there is always an ambiguity that whether that can convert it itself into that can convert into hardware or not. So that's why it's only a subset, and you also always write to always you have to see using the code and then see whether it can be converted into hardware or not. There are many syntaxes which cannot be converted into hardware. Simulation is another interesting thing that you see. Most important thing you have to understand in the simulation is that it is going time by time. So every time you are simulating only one delta step. Okay, so what do I mean by delta step? That let us say something is happening at time equal to 0. So you will try to compute everything, whatever is happening at time 0. And you're also trying to compute what would be assigned in future. And then you'll try to keep a queue of all of those things. And whenever that time will come, those things would be assigned. So this way simulation would go from one delta cycle to another delta cycle. I understand this explanation is very concise. So maybe sometime we can have a special workshop which would focus on the simulation topic, and then we can have a couple of lectures on the simulation, and we can also then in that case practice how to design simulators. Oh, there are some practical questions. Okay, so what are the basic codes we can start with? So this particular course, this particular module itself gave you a guiding suggestion that you first try to design simple adders, multipliers, and then try to introduce pipelining here or multiple cycles or introducing this FSM there. So this way we would be able to start with small things and we can go to larger or basically bigger codes. And then maybe once you are acquainted with your sequential design as well as but don't go with the books. So don't go with the books means don't go with the examples which are given in books. They're even smaller. So start learning with them and then try to design your own accelerators for one application or the other application. Aniruddha is asking, in Verilog, we have seen very little sequential circuits. Are there any resources that I can use to learn more about this? I am also searching. So whenever I'll come through some good resource that is you implementing sequential circuits, then I'll share. Sure. I have your email ID. Ankita is asking, what is the difference between verification engineer, testing engineer, design engineer? Okay, that's an interesting question. And this cannot be answered easily because it's a part of marketing of the company. So, for example, if they understand that students don't like the role which is written as verification engineer, so they can term it as a design engineer. So the most important thing is what role you are into, what is the job you are actually doing, not the title. So this is very important. This is very common misconception in industry that if you are return manager, that you are managing people. So similarly, verification engineer is not important. That if you could be a design engineer but doing a verification job. So and design engineer would also, like, whether you are doing analog design or digital design. So most of the time, uh, you would require this in the design process, you would require engineers at multiple stages. One stage, you would be writing RTL code, okay, or fixing it or debugging it. So that is one stage. The other stage is uh, you would have RTL code from different places. So that's how most of the SOCs are designed today. So they take IP from different places and they glue them together. And to glue them together, you need to write the interface, and that would be again in Verilog because both of these codes are in Verilog. So that's also a part of design engineer. And after these things are done, then you will have the next process of synthesis. And in synthesis also there will be multiple processes. You will be looking for your clock period, and then again doing back annotation. Okay, and some people may be doing some kind of a power analysis. And if your chip also have this additional things, which is let's say power gating, not clock gating, power gating, or something like DVFS. So then this power verification become difficult, design will become difficult, the cells are different. So all of those things again would be required to fix and test. um, they would be again probably in the role of design engineers. And then verification part, verification is now, right now it's a very big domain because verification is difficult, first of all. And second thing, verification also involves so many different things, not only writing test vectors, but doing this whole verification methodology, that also would be discussed in one of the module here. So that's a good thing. So you can ask the same question there also. So verification engineer could be doing emulation, could be using this UVM methodologies, could be writing test vectors, could be simulating Verilog, and could be handling with these FPGAs or this emulation boards. So there could be a wide, different variety of roles of these verification engineers. You could also be designing verification IPs. So roles are variety in, but the understanding you in certainly when you are doing designing, you should have an understanding of verification. When you're doing verification, you should have a understanding of how RTL works or how design works. Okay, so there is another question. Yes, there was a project related to lift control system. So I have skipped that lift control system in favor of GCD because lift control system was essentially an FSM. Okay, and FSM we have covered in day 4. So that's why we could have, this is my mistake that my planning was not good. So I'm sorry about that, but lift is more towards an FSM, and I wanted to cover much bigger thing. That's why I opted for GCD and high level synthesis for today's lecture. So this was a very sudden decision, and this lift control system could not have been covered for this 2-hour duration. That was also another reason which I had to skip that. Thanks, but for asking this question. So it's a clarification from my side and also apologies from my side. How do we write truth table in Verilog? Okay. So Naveen has already answered your question by doing UDPs. Okay. Um, what is difference between Verilog and system Verilog in terms of industrial demand? System Verilog means verification. Verilog means design. That's a practical difference. So whenever you're using system Verilog, you would be using it for verification. This system Verilog can be good tightly integrated with all the verification methodologies like UVM, etc. So if right now, at least in India, if you are doing a verification, then you would be much more in demand than if you're doing RTL, because number of RTL engineers would be less and number of verification engineers are much more. So in terms of demand, system very low, not only system very low as very low, but understanding how it can be used for verification would be beneficial for from your perspective. Uh, Vaishnavi Deshpande is asking for finding GCD, can we use for loop later finding mode of two numbers and will it work in Verilog? So here also we have used loop. So instead of finding mode, we are doing subtraction because subtraction we find easier. For finding mode, there is no other way but to divide. Okay, so essentially what we are doing here is in our algorithm, what we have done is we are doing division by using subtraction rather than mode. So if you would like to use a mode operator or a division operator, then we can use that also. Otherwise, for loop or while loop, they are more or less same. So essentially we are doing looping here also. Uh, Nandini is asking, can we get RTL schematic in EDA playground as in Xilinx? Actually, EDA playground is no way equivalent to Xilinx toolchain. EDA playground is just for writing initial Verilog code, compiling it. That's it. It doesn't provide any kind of a synthesis support. So for synthesis support, if you want to, and unless you do synthesis, you cannot do RTL schematic. So that's why if you want to do synthesis, you have to use Xilinx or Synopsys or Cadence tools. EDA Playground is just to start initiating yourself onto Verilog, and we use this as a platform in this particular session and internship because I understand that not everybody could have access to these compilers. I have no idea about analog design. I never worked onto analog design, Gaurav, so I can't answer your question. Uh, the other question is how RTL code is converted to gate level abstraction. So this RTL code, this I answered partially in as a part of previous question, one of the previous question. RTL code is converted to gate level abstraction by logic synthesis. Okay, so the input to convert an RTL code into gate level abstraction is the library which you would use as a gate level abstraction as a gate level. So these libraries are sometimes called standard cell libraries. These libraries will come from some web fabrication vendor. So either it will come from TSMC or it will come from UMC. So they will create those libraries, and these libraries will be part of a package, and this package would be given as an input to your synthesis tool. Now, with that input, you know that which all gates are present in your fundamental circuit. Now, as I told in the starting of this discussion, so your data flow and structure will have one-to-one correspondence with those gates. Even if those gates are not there, they're easy to convert bigger gates into smaller gates. Okay, for example, if you don't have 9 input OR gate, you can convert using 5, 2 or 4 3 input gates. Okay, so data flow to gate level is easy, but for behavior we use high level synthesis or behavior synthesis, which is again a part of Verilog compiler toolchain. So they will try to intercept, and there are standard rules. They will say that, for example, if else would be converted to mux, and if there is a at the rate statement, and there is a postage written, then it would be any write would be converted to a register. So there are certain rules which would be followed, and it would try to create a state machine automatically, and the synthesis tool will generate first an RTL, then gate level netlist for you. Okay. So if is required to do synthesis and download this design onto FPGA, will it support? Yes, as I said earlier, if you want to download onto FPGA, then you cannot avoid. You have to have Xilinx toolchain. EDA playground is limited only to simulation. Yes. For synthesis, you have to have FPGA, and you want to finally burn things into FPGA, then the particular FPGA you are using, if you're using Intel FPGA, you have to have that Intel FPGA chain, if tool chain. If you're using Xilinx FPGA, then you have that Xilinx tool chain. Um, One more question, that can we use block in data flow, always block in data flow modeling? No, we cannot use always block in data flow modeling. How to model clock signals in data flow? So what are you doing with clock? So if you're generating clock, that you can do, you can process clock, but your clock dependencies, or basically when you write at the rate postage clock, what does it mean? It means that particular event, that particular process would be initiated only at the positive edge of the clock. So that essentially means that you are writing, whatever you are writing is essentially a register. That's what your behavior model would be whenever you're writing at the rate postage clock. And if you are writing any other thing other than this as a sensitivity, that can be either modeled using data flow, or you can write behavior also. For example, if you want to use comparator or adder, you can say the two inputs A and B, you can write at the rate always at the rate A B, and add A plus B. So this is sufficient. Our next module is on our next module is that only for analog mixed signal. Yes, that's have suggested by Gaurav. Abhishek sir, can you tell about the format of tomorrow's exam and type of questions that can be asked? It would be objective type exam, and the test will have two type of questions. One would be based on understanding what you have got, and the other would be application of that understanding. So understanding essentially means that let's say we have discussed some data flow features, data flow modeling features. So there could be some question on data flow, which could be if you know the data flow concept, then you can answer it immediately. The other would be application type, so which mostly involve that uh, there could be a application onto some design, or application onto some particular method where you have to apply that concept and then answer. So it's a typical exam what we take in IIT or NIT. Any online course to get better on Verilog? Is NPTEL course good enough? I have not myself gone through NPTEL course, um, so I cannot answer it correctly. The data, the data path and control signal slides of GCD can be modeled only after having RTL. Am I right? Yes, 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 yes. So, Nandini, you are correct. So basically the approach, this is the approach we have taken. We were trying to design a GCD in a RTL manner. So that is why we have broken things into operations, created a data flow. RTL will come little later, because we still need to decide when we design a state machine, then we decide that how many states would be there, how many cycles would be consumed. That would essentially mean RTL. Yes. Is there any limitation to synthesize procedural continuous statement? Procedural, there is no continuous statement. Either they are in procedural, either they are blocking or non-blocking statement. And as far as statements are concerned, blocking or non-blocking, there is no limitation on synthesis. So synthesis limitations will come because of multiple reasons. Sometimes, let's say, if you have a feedback path, so those kind of things, your synthesis tool will say it cannot synthesize. The other things are some constructs, for example, files, dumps, all those things are not synthesizable constructs, although they're part of Verilog, so they're more for verification. So otherwise, a major portion of Verilog is synthesizable. So if you read any Verilog book, so they will clearly specify that this particular syntax or this particular command will not be synthesizable. That's it. Otherwise, yes, more or less everything can be synthesized. Sometimes our designs are bad, so your synthesis tool will tell that it cannot be synthesized. So if I use a sensitivity list without clock, can I still call it a data flow model? No, we cannot call it data flow model. So you can always say that at the rate always and put a star. So that means everything, whatever is sensitive, it will be initiating. But the reason we cannot call it data flow is because within the always block, all the statements happens sequentially. So if you are using non-blocking statement, then then overall you can achieve the same effect. Yes. Uh, the follow-up question is, if I want my data flow model to follow a rising edge of the clock signal, can I do it? Should I go for behavior modeling? Yes. Yes. You have to go for behavior modeling in that case.
हाँ सर हाँ सर हाँ ठीक है मैं join हूँ
Okay, so if there is no more question, then we can call it a day. And thank you very much uh, for two things: for giving me opportunity that to talk to you, and second thing, to listen patiently and complying with the assignment. And the response was especially encouraging. So because the response was encouraging, so it was also giving me motivation to work further to give you more interesting ideas as well as examples. Okay, so yeah, with that we can call it a day. Thank you very much.